Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Professor Clark. Thank you for meeting with me during office hours.
Good afternoon, Daniel. How is your research on chaos theory applications coming along?
I am trying to connect the mathematical concepts to real forecasting problems in weather and economics, but I am stuck on how to explain the limits of prediction clearly.
That is a central issue. Chaos theory in mathematics gives us tools to analyze deterministic systems that nonetheless behave unpredictably. For weather, we can discuss Lorenz and the butterfly effect. For economics, we can discuss nonlinear models and how small shocks can amplify.
Right. I know the Lorenz 1963 model produced a strange attractor and showed sensitive dependence on initial conditions. How do I translate that into a practical statement about weather forecasting accuracy?
You can say that the Lorenz model is a simplified mathematical example that demonstrates sensitive dependence. In real atmospheric models, the same principle applies. Small differences in initial state, such as slight temperature or humidity changes, grow exponentially at a rate given by Lyapunov exponents.
Lyapunov exponents measure divergence of nearby trajectories, so a positive exponent means chaos and rapid loss of predictability. How long is the predictability horizon for weather using that idea?
In practice, with current models and observations, deterministic weather forecasts are useful out to about 7 to 10 days for specific patterns. Beyond that, the exponential growth of small errors makes single deterministic forecasts unreliable. That is why meteorologists use ensemble forecasting to provide probabilistic predictions.
Could you clarify ensemble forecasting in mathematical terms for my paper?
Ensemble forecasting means integrating many model realizations that start from slightly different initial conditions or parameter choices. Mathematically, it samples the phase space near the analyzed state. Instead of one trajectory, you get a distribution of trajectories, which can be used to compute probabilities and confidence intervals.
So ensembles do not remove chaos, but they manage uncertainty by showing likely outcomes. Would that be a fair conclusion?
Exactly. Ensembles do not eliminate sensitivity to initial conditions. They translate deterministic chaos into probabilistic forecasts, which is essential in operational weather prediction.
How does this compare to economic systems? Financial markets look chaotic in charts, but some economists say markets are stochastic rather than deterministic chaotic systems.
Economics is more complicated. Many economic models are driven by both chaotic deterministic dynamics and stochastic noise. Some macroeconomic models display bifurcations and cycles that resemble deterministic chaos. Other phenomena are better described by stochastic processes. The key mathematical question is whether the apparent irregularity stems from high-dimensional nonlinearity or from randomness.
Are there concrete case studies where chaos theory improved economic forecasting or understanding?
Yes. One example is the use of nonlinear dynamic models to explain intermittent volatility in exchange rates. Researchers have used regimes with strange attractors to model boom and bust cycles in commodity prices. Another example is agent-based models, where nonlinear interactions between many agents produce emergent chaotic patterns that mimic real market volatility.
You mentioned bifurcation. How would I explain bifurcation in the context of economics to a general academic audience?
Bifurcation is when a small change in a system parameter causes a qualitative change in long-term behavior. For example, a change in interest rate policy could push a system from stable equilibrium to periodic cycles, or to chaotic fluctuations. Mathematically, you can illustrate this with simple nonlinear difference equations and show parameter thresholds where behavior changes.
What about the challenge of distinguishing chaos from random noise in economic time series?
That is a major methodological challenge. Techniques include calculating Lyapunov exponents, testing for determinism using surrogate data, and reconstructing attractors via delay coordinates. But real economic data are noisy and often short, which makes results less definitive than in controlled physical experiments.
In weather science, we have longer observational records and can assimilate data continuously. Does data assimilation reduce chaos?
Data assimilation does not remove chaos, but it reduces initial condition error by combining observations with model forecasts. That extends the useful forecast horizon somewhat. Still, because of positive Lyapunov exponents in atmosphere dynamics, there is a fundamental limit to predictability.
For my presentation, I want to show how Lyapunov exponents, ensemble forecasting, and bifurcation analysis interrelate across weather and economics. Any advice on balancing mathematical rigor with accessibility?
Start with a clear definition of sensitive dependence and Lyapunov exponents in plain language. Use the Lorenz model as an illustrative mathematical example for weather. Then present one economic case study, like exchange rate modeling, showing similar mathematical diagnostics. Emphasize that applications differ because of data quality and external forcing, but the underlying mathematics of nonlinearity and attractors is shared.
Should I include a brief mathematical appendix with equations for Lyapunov exponents and a simple bifurcation diagram?
Yes, include an appendix for readers who want technical details. For the main talk, use visualizations. Show a Lorenz attractor plot, an ensemble spaghetti plot for weather, and a bifurcation diagram from a simple economic map. Those visuals make the concepts concrete.
One more question. You said earlier that ensembles translate chaos into probabilities. Could you give a concise sentence I can quote that captures that idea?
You can quote this. Ensembles do not eliminate chaos, they sample possible evolutions so forecasters can express uncertainty as probabilities rather than false precision.
That is perfect, thank you. I feel more confident linking the math to concrete forecasting strategies now.
You are welcome. Feel free to send me a draft of your slides and appendix. We can refine the balance between math and applications.
I will. Thanks again for your time and the case study suggestions.
Listen again to part of the conversation, then answer the question.
Ensembles do not eliminate chaos. They sample possible evolutions so forecasters can express uncertainty as probabilities rather than false precision.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.